Hi everybody, this is Mrs. Ellsworth. Today we're going to be talking about two basic things. We're going to be talking about the primary colors of light, the primary colors of pigments such as paint, and then we're also going to be talking about when you are aiming at a fish with spear, that you have to actually aim low, and there's physics is involved in that too. Okay, so now that I introduced that, let's go ahead and go back and look at the light. Okay. Here's light. This is pigment. So this is paint. Have you ever heard of primary colors being yellow, red, and blue? Well, they're actually not. The primary colors that make up all the whole color spectrum are actually magenta, yellow, and cyan. So if you go and you mix these two colors together, when we do this in the classroom, when we mix these two colors together, we get more of a blue, sometimes a blue-violet, but we don't measure out our colors and we don't make sure that we're mixing that part of our circle in the perfect 1-to-1 ratio. Anyway, so this is supposed to be just blue, but it quite often ends up being blue-violet. Okay, when we mix yellow and magenta together is red. Red-orange it says here, but it's usually just red in our classroom because we mix up these paints and we look at them for the primary colors of paints or pigment. I hope that you're writing these circles down and taking notes on these so that it's available for you on the test. Okay, when we go and we mix yellow and cyan together, we get green. And so these three colors, when we mix them equally together, they subtract all the colors so that you get black. But that's not, we're always disappointed in the classroom. We always get a brown or else we get a gray. Or else we get between brown and gray. It's just kind of an ugly dark color, but it's not too dark either. So mixing these up in the classrooms, we're always a little bit disappointed that it doesn't turn out perfect, but it is something to also go by to help us understand how the colors come together. Of course, if you're measuring more cyan than yellow, then you're going to get more between a cyan and a green. So I mean, it melds in to one another just like rainbow. Okay, so notice that green, red, and blue, green, red, and blue. So notice that there is a relationship between these two. Also with yellow, magenta, cyan. Yellow, magenta, cyan. So there's a relationship between the two. And sometimes it's difficult to remember which is which. You guys are fortunate this year with the COVID thing because you get this for you get to use your notes. So kind of fortunate for that thing. One fortunate thing of it. Anyway, so let's go ahead and look at the additive colors. Now, when you talk about light, the red and the green and the blue, I was always struck how when you took red and green and added them together, you got yellow. Maybe because before that I would always get the pigments stuck in my head. So how can you get a lighter colored light by adding two together? And what you're doing is that you're adding more light together, so you're going to get more colors from it. And so with this one, it kind of like struck me odd. Okay, and I think it does most people. But when you go and you add red and blue together, you get a magenta. Well, that kind of makes sense to us because we've always thought about red and blue being added together. You get kind of a purple color, but it's magenta with light. And then, of course, when you add blue and green together, you get this pretty cyan color. Anyway, then when you mix all the light together, and that makes sense because when you think about all of the rays coming from the sun, that you get white light. Okay, so it's adding all the different colors of light and you get this additive white light. So that is the color spectrum. And from this information I have, you can stop this video and then come back to it tomorrow and look at why, look at refraction here. Or you can just go ahead and finish it up because I'm not going to take real long on refraction. But with this information here is kind of introducing what you need to do with this lights video and worksheet that we're doing in class today. Okay, so moving on, I'm going to finish this video now. Okay, so what are we talking about with this? So you see a fish and it makes sense that you would just aim at this fish, but the fish is actually down here. That's because of refraction. Refraction bends light rays. Okay, what happens when light goes into a different substance is that it slows down the light rays. It isn't going to be traveling at 3.0 times 10 to the 8th power meters per second. It slows it down just a smidge of a smidge. And so that's why you see bent spoons. That's why you see, why you can see this is used as a lens, and so you can see the things around you. That's why when you go to a pool, the lines are not perfectly straight, are they? Because of the refraction and at the angle of the waves on top of the surface, how it slows it down and makes the light rays bend at a different angle. Okay, and then there's those, lots of people, they like doing those fun little tricks on your eyes with glasses full of water. And so that's kind of cool too, because it bends the light rays. Okay, so here we go. We got a man sticking a pencil in there. It bends it with the light rays, and here's a joke about it. So what the heck? Anyway, in classroom, we always go and we take a acrylic block, and we look through it with a pencil, and we find that our bottom of our pencil is not attached to our pencil, you know, when you look at it through the acrylic block, but we are not able to do that here. So I'm going to go over some slides rather quickly because we're not doing it during the COVID-19 time. But I want you to think about something here for a second. If I had a 2-carriage wheel thing here, and here's cement. Okay, this is talking about a lawnmower, those old-fashioned ones that don't have a motor on it. They just have the clipping blades. Anyways, so when your wheel hits this on the right side, it's going to make it naturally want to turn to the right. Okay, it's going to make it naturally want to turn to the right. Well, that's actually the same thing as light rays coming into glass. Okay, and so it makes it want to change its direction because it slowed down part of the ray and it turns it. And we find that this is an effective model that describes how it bends. Okay, and there's a silly picture there. So what happens is that lawnmower or that wheeled cart, it comes and it hits the grass, okay, and then it turns to the right. Okay, well, it's the same exact thing with the incident ray going into a block. Well, if you go and Google this, you'll see that you also get a reflective ray coming off here too at the same angle. Of course, angle of incidence and angle of reflection. But some of the light also goes through the block. And we could see that in the lab. And so then when it goes back into air, then it's going to bend away again, away from the normal. And so then the ray that comes out of there is at this parallel to the incident ray that came in. But now it's been knocked off a little bit because when it goes through glass, it actually curves towards the normal. And so here's our normal is perpendicular to the surface. And so when it goes into a substance that has a higher index of refraction, then it'll refract towards the normal. And then when it goes from a higher incidence of refraction to a lower, then it bends away. So it's kind of cool. So here again are those angles of incidence, angles of refraction in this case, not reflection. Okay, so that's kind of cool how it goes through different ones. So we would normally do a lab, and so I'm going to go through these kind of quickly here. Okay, so this is gone. There we go. So this is kind of cool because this is the refractive index of refraction. So it's kind of neat. So when there's no error, that's what we go and base everything off of. That's what we use for kind of like a control. We label that as 1, so we're able to come up with values for everything else. So then glass has got quite a high incidence of refraction, so that's why it curves through it. That's why when I was a kid, you know, you get glasses and they were made of glass and they were really thick because it doesn't have an incredibly huge incidence of refraction. And so then they start coming up with these polycarbonate ones that are have a higher incidence of refraction. That's cool now because now my glasses can be so much thinner because I have such poor eyesight that they used to be, well, they used to call them Coke bottle glasses because, you know, the old-fashioned glass bottle would be a really thick bottom. And so so now it's kind of nice because everybody can wear thin glasses because of the higher incidence of refraction of polycarbonate. Okay, so you can look at different things: sapphire, water, they would all bend towards that normal when you go from air into a substance that's got a higher index of refraction than air. Okay. So when you've got one that's got a higher incidence of refraction, it bends towards the normal even more. Now, there are some things that people always talk about, that is, they talk about this critical angle. So when you're going through a block, okay, and you've got you're starting right here, your laser beam is printed right here, and so then it goes straight through, and you keep on going at different angles, and it will bend away from the normal here, and then you all of a sudden get to an angle where no more of it comes out of the block. It just all stays inside the block and continues to be, because now the surface become reflected on the inside of the block. So it's kind of different. But after you know these type of things, you actually see this happen occasionally, and then you think like, oh, that's reached that critical angle. Okay, so we're going to skip that video talking about why is this pole bending, and because of refraction. So when it goes into light from our eyes go into the water, then it refracts it. So let's talk about that fish again. Okay, so he's seeing observed, but we know that the light rays bend towards the normal, which is up and down here. So what we're actually seeing is a fish that's down here. And so that's why they always tell you to aim low whenever you're spearfishing. But if it's in such a shallow creek or something like that, which it usually seems to be, then this isn't too high of a change here, because it's more shallow. You know, they're not going to be too far off. And here's just another example of how our eyes can play tricks on us because of the angle that is being refracted. Okay, we did that. We would have done that in class too. Okay, what I'd like to say also is that lenses are the whole idea of refraction too. And I alluded to that when I talked about my glasses being much thinner now than what they are. And so when you go and change the surface of your cornea on your eye, then that changes how well that you see. But I just wanted to briefly talk about lenses. We actually try to burn a hole in some tissue outside and normally in our class when we hold up the lenses. And when we do that, I just wanted to show how light is coming in. Now the focal point we look at on the other side, and we would typically do some labs with this. A lot like what we would have done with a mirror lab too in the classroom. But it just kind of shows how that this now makes it so that if you had some sort of lens, you don't have this type of lens on your glasses, but that how it brings a focal point to where your eye sees it with corrective lenses. So what I was going to say is that you're trying to see the images on the back of your retina of your eye, and so corrective lenses goes and changes that. So like if you're nearsighted, it's not going to be at the focal point. It's going to be in front of the back of your eye. So it's because your eye is longer, and so you need a corrective lens to get that image placed on the back of your retina. And if you're farsighted, then now you've got also a short eye, and so now the focal point would have been behind there, so you'd need a corrective lens in front of there to help change to where that focal point is on the back of your retina. So it's quite interesting when you think of it that way. Here's a simpler drawing of that. But we do not do ray diagrams this year. It's a short year, and so that's pretty much all I'll talk about refraction. Refraction will actually not be on your test. It's just the basics of it, that it's bending the light rays as it goes from one surface into another. So that's basically it. So I will see you later. Bye-bye.